So I'm Vincent Darrigrand. I'm a postdoc at IRIT in Toulouse. And today I will talk about some new developments that have been done in domain decomposition method, coupling with a sparse direct solver. And especially I will focus on novel feature of sparse direct solver through this domain decomposition method. This is a work done in collaboration with Alfredo Buttari, Daniel Rees, and Pierre Jolivet. So first of all, I would like to thank our collaborator from MEMS side, such as Patrick Amestois, Jean-Yves L'Excellent, and Chiara Puglisi, as well as Theo Marie in Lipsis. And from the Barcelona side, I would like to thank Adria Quintanas, Guillaume Muzo, and Herbert Owen. So what we are dealing here are the resolution of linear systems, where the matrix can be potentially large and sparse, such as this wing blade that we have been working on with people from Alya. So usually to solve those type of system, there are two solutions. Either you go with an iterative solver. Those are cheap, scalable, but they are highly param dependent. And on the other side of the spectrum, there is direct method that are robust and precise, but can be prohibitively expensive. And in the middle, there are some hybrid method. And one of them is domain decomposition method coupled with direct solver. And this is what we are looking at today. So in few words, domain decomposition method can provide a useful preconditioner where you just need to solve the problem on subdomains from the whole domain, so it should be cheaper. And on top of this partition, you can build a course correction that will help the convergence of the solver. And there are many type of course correction. In Alya, for instance, there is an arbitrary deflation, and in the other software, HPDDM, it's a local basis of eigenvector through a GenEO solver. And what we are doing today is to look at what's happening when this resolution is done with a direct solver. The direct solver we will use is MEMS, which is a multifrontal algorithm. And the multifrontal factorization needs to compute an elimination tree from the graph of the matrix. And then for each of the multifrontal matrices, it will perform a partial factorization from the bottom of the tree up to the top of the tree. The complexity of this method is quadratic with a number of unknown. So with that complexity in mind, we can devise two strategies for the preconditioner coming from domain decomposition. Either we go with very small subdomain, so we can have a low complexity, but potentially it can converge very slowly. And on the other side, we can devise larger subdomain, but with a higher complexity, but on the other hand, it will converge faster. A simple example on a toy problem, not really realistic, but still it illustrates well what we are facing, is there are two configurations. Either we go for the configuration recommended by direct solver experts, which is 1 MPI per socket, and the other configuration, which is with full MPI, and so it's with 1 MPI per subdomain. And we see that even though the number of iteration is doubled from one configuration to the other, the time spent in the solver is divided by 2 for the full MPI configuration. So the question is, with the new tools at our disposition, such as the block low rank approximation and the 3 multithreading, can we reduce the complexity and perform faster computation to be able to reverse this tendency? So I will just describe in a few words those two methods. So first, the block low rank approximation, which consists in, when considering a multifrontal matrix, we try to compress a block of this matrix into a product of two vectors. And we try to do that respecting some tolerance. So the idea is the blocks that can be compressed are the blocks that represent interaction between two subdomains that are far away, subdomain from the multifrontal matrix. And doing so, we ensure that the singular value decays very fast, and we can perform such compression without losing too much precision. So this is the idea, to control the precision. And doing so, we can reduce the number of flops from the square of n to n to the power of 133. So this it could be a considerable acceleration. The other tool is the tree multithreading. The idea is to mix node parallelism with tree parallelism. On the bottom of the tree, we will solve concurrently all the frontal matrices with one thread for each. And on the bottom of the tree, on the top of the tree, sorry, we will solve each block one by one, but with a multi-threaded blast operation inside. What's really interesting with that method is, especially with the block low-rank compression, since those blocks are compressing less than the top one, the multi-threading can bring a significant advantage. And especially for the solve phase, when you have to do a lot of solve phase, since this part of the tree is quite significant, it can bring significant performance improvement. If we go back to our Helmholtz toy problem, we see that when still in the configuration 1 MPI per process, which is the one we want to improve, when we enable the tree multi-threading, we see that we can divide the time spent in the solver by almost a factor of 2, a bit more than a factor of 2, and to drop below the full MPI configuration. And if on top of that we enable the block low rank, here it's done with a tolerance of 10 to minus 10, so the loss of precision is not significant and only produce a small, a bit more iteration for the DMRS. We see that we can even further reduce the time spent in the solver. So with those results in mind, we go to some more, say, realistic application, such as this wing from a wing generator. And the problem here is a nonlinear time-dependent elastic problem. And it's a deformation of the wing when there is, on the top of the wing, a displacement that has been imposed. So for this configuration, for this problem, the discretization is around 15 million DOF. So what's available in Alya is an iterative solver. Here we use a GMRS solver, preconditioned by restricted additive Schwartz with a deflation. The coarse space is built with that deflation, which is an arbitrary agglomeration of the mesh. And this iterative solver will be called again and again on each Newton-Raphson iteration for each time step. So there is a lot of solves involved. So for a given configuration, here it's 400 MPI, which means 400 subdomains on Mare Nostrum. And just for one time step, we have quite a lot of GMRS iteration, and the solve time is like this, almost 400 seconds. What is important to note is the LU package we use, as Herbert mentioned, is an in-house LU package. So the first thing we've done is to replace this LU package from Alya with MEMS. And we see that the timing significantly reduced. So we want to try what's happening if we enable multi-thread technique here. So I just present the ways to thread, but this illustrates well the tendency. If we increase the number of threads, it's happened the same thing, which is the number of iterations remain globally constant, not exactly, but quite constant. But the solver spent more time for the resolution. And this is because we can control the number of iterations thanks to the course correction. If there is no course correction here, and the number of iterations from there to there will increase dramatically. So with that, the best configuration is the full MPI with MEMS as LU solver. And it's important to note here that the sub-problem are way too small to gain anything from the block-Lorentz compression. And if we let run this problem for 10 time steps, we can observe that the replacement of the LU from Alya with MEMS gave a really good improvement in the timing. If we look in detail on the time spent in the solver, we can see that where MEMS is much more efficient is in the factorization, a bit also in the solves, but it's not significant. What's really important here is on the factorization. Then if we look at the multi-threaded case, we see that the factorization time didn't grow as it could grow. Indeed, each subdomain is double the size. So the complexity should quadruple in full rank. However, thanks to the tree multithreading, we could smooth out this extra complexity. But still, it's not enough to beat the full MPI configuration. Then we wanted to try this problem with HPDDM. HPDDM is an implementation of domain decomposition preconditioner, which involve classical RAS and the course solver, the course correction is computed with, as I said before, with an eigenvalue solver and a local basis of eigenvalue. You have to know that the course problem here will grow linearly with a number of subdomains. So at some point, it could, when the number of subdomains is way too large, this step could cost a lot, since also this problem become more and more dense. So there are some tools implemented in HPDDM that enables to tackle this problem. But for our case, we don't have this problem since we use only a few cores. However, the HPDDM interface is not yet done in Alya, so we had to handcraft some problem that could simulate somehow what's happening with the solid problem we solved with Alya. So we designed a linear elastic problem with heterogeneous media, and this problem was chosen to have 61 million DOF, and such that MEMS would run out of memory when we try to solve it directly on 10 computing nodes at CalMIP supercomputer in Toulouse. And the conclusions are quite similar to what we've seen before. However, since the problem is quite large, each subdomain has a large number of DOF, degrees of freedom, and the block-Lorentz can provide some gains. Indeed, we see the difference between those two configurations, where the only difference is the block-Lorentz enabled, is that we reduce the time spent in the solver by a factor of almost 10%. And as before, since the course correction does a great job in controlling the number of iterations, the full MPI is the best configuration. Here also, I only put the second best results. If we increase more the size of the subdomain, we will lose more performance. If we look in detail to the timing in the solver, as was mentioned yesterday for Mafi's problem, For Mathis solver, the most of the time is spent in the eigenvalue problem. Here it's the red, the blue, and the green part, where the green part is the total time spent in the solves for the eigenvalue solver. And this is where, with the block-law rank activated, we are able to gain those almost 10%. A bit also in the solves from each subdomain, but it's not really significant since the number of iteration is quite reduced. And as before, when we enable the multithreading, we see that the factorization costs more, but it's not quadrupled as expected. So the multithread does a great job on that, but in that case, it's still not enough to reduce below the full MPI configuration. So in conclusion, there are two things we have to know. The first is MEMS, following those results, MEMS will be used now in production runs in Alya, which is great since for the EcoCoE project, we wanted to accelerate Alya. And then it's a message for practitioners out there. If you have a way to control the number of iterations, for instance, with course correction, then do it. You will obtain the best result with full MPI, and you can eventually use block-law rank to reduce the cost of the resolution on each subdomain. And if you cannot control the number of iterations for whatever reason, then we would advise you to use larger subdomain and to couple it with block-law rank and multithreading, and it will surely provide you with better results. And as a future work, we want to look what's happening when the blade will break. And in that case, the course correction may not be sufficient to reduce the number of iteration. And in that case, maybe the larger subdomains will become more competitive. And the next step we want to do with Alya is to plug HPDDM and to be able to compare both methods. Since with HPDDM, with that course correction, we should be able to control the number of iteration and hopefully reduce those 2,000 iterations to something less. That's it for me today. Thank you for your attention.
Thank you, Vincent. So are there any questions? Okay, since there doesn't seem to be any, thank you again, Vincent. This will conclude today's last talk. Oh, Herbert, just so that.
Yeah, sorry.
Okay, go ahead.
Yeah, I took a minute to find the raise the hand. So very nice talk, Vincent. Thank you. So
thank you.
It's interesting, and well, this it could be interfacing one further code with Alya. Well, this, if resources permit, is very interesting to me. And from what I've talked with Andrea, the option is to do it through PETSI, and this opens like a nice window because it will give us, well, I would say that PETSI could be kind of a reference when we test against other solvers, when we test against, I don't know, AGMG, PS Plus. PETSI is very well known and it has lots of solvers inside. One of the things that has restrained me from doing PETSI, apart from the lack of resources or time, is that then you need to know how to configure it. But well, in this case, that wouldn't be a problem because we would be using your solver. And this is very interesting to me. And here, we are exploring the possibility of using this HPDDM. Now, this HPDDM is an iterative solver in some way, coupled to a direct solver, so it's in the middle. And here, we are thinking about using it for solid mechanics problems, but we could also use it for fluid mechanics problems. Actually, I understand it's similar to what we have in Mathis.
Yeah,
and well, there's a lot of opportunities that that appear of how to use it. Perhaps we could even try to use PAFIs that we already have interface to try to solve one of these solid mechanics problems and see if it gives some advantages.
Yeah,
But
of course,
well,
it would be
in
very
any
interesting
case,
to do
thank you
that.
very much. It's
Thank you.
very nice new lines.
Thanks.
Thank you, Herbert. Okay, as I was saying, this concludes the series of talks we've had for the last 2 days.